So first let us simulate our design. So to simulate, we are going to call iVerilog dff underscore const 3 dff underscore const 3 tb underscore dff underscore const 3 dot slash a dot out gtk wave this vcd is our value change dump file. So let us open that. So I'm going to go and pull the Q1 also, because Q1 is not a primary output of the module. It will not be visible to us. So I have to go into the unit under test to pull the internal signals, because otherwise at test bench only Q is available, right? Reset. Let me pull Q1. Let me pull Q. Let's go to 100%. Here you go. So let's zoom in the region of interest. So if you see here clearly Q1, let's exactly the next clock cycle, next passage after reset deassertion is where Q1 goes 1. The next passage after the reset deassertion is what? Q1 is going 1. This is the passage after reset deassertion. And on that edge, Q goes 0. On that edge, our Q is going 0. And on the next clock edge, Q is going 1. So you see Q going low for 1 clock pulse. And that is not in some clock, exactly the same clock pulse where Q1 rises. So the pulse in which Q1 rises for 1 clock cycle duration, Q goes low. This is what our simulation is revealing. Let us see what our synthesis says. So let me load uses, read liberty hyphen lib dot slash mylib lib sky 130 lib read verilog dff const 3 synth hyphen top dff underscore const 3. So as expected, it should be inferring 2 flops. Let's see. Yes, in the statistics I can see that 2 flops are inferred. And dff lib map hyphen liberty slash mylib lib sky 130 lib. So as expected, it has read all the DFF cells. These are the available 20 or so flops. And then we can say abc hyphen liberty lib mylib lib. So you can see it has mapped it has used the inverter cells, 2 inverter cells, and you can see it would have used the flop also. If you scroll above, you can see it would have used the flop. Let's do a show and check. Yes, we can see that the flops are being mapped. So we are able to see the DFF now. Now kindly note, in the previous case when we did the show without the ABC, we saw both were simply connected to reset, correct? Now, but we are seeing actually a Sky 130 library standard cell inferred here, and see, this was our expectation, correct? The flop was a set flop. The first flop was a reset flop, and the second flop was a set flop. The first flop is a reset flop. The second flop is a set flop, and the output of the first flop is connected as the D pin to the second flop. So the Q pin of the first flop is connected to the D pin of the second flop, and we can see the same clock signal is connected. And here this is a reset bar and this is a set bar. That means the set is active low signal and reset is active low signal, but we have used active high reset and active high set, so there's an inverter in the path. This is what we simulated, and this is what we are seeing in the synthesis as well. So with this, we understood the synthesis, the sequential optimization that's happening, and not every flop which is having a constant at the input will get optimized. We need to look at the reset and the set connection to the input of the flop and see whether the Q is getting a constant value or the Q value is going to change. That's a very key important point to understand this, and based on this, you guys would be working out the DFF underscore const 4 and const 5 as part of lab exercises and trying out. I want you guys to try out all these three things also, and then try out DFF underscore const 4 and const 5 as exercises. Okay, thank you.